Hello everyone, welcome back to AZQs. So last time we was trying to look at the chemical equilibria, and under equilibria we have a series of topics. So have topic one, the phase equilibria. Topic two, acid-base equilibria. Topic three, chemical equilibria. Topic four, redox equilibria. So last class we tried to see at phase equilibria and acid-base equilibria. So today we're going to see chemical equilibria. So consider the reversible reaction below. The reaction has N2 gas plus 3H2 gas giving 2 ammonia. This reaction has attained equilibrium. For a reaction to has attained equilibrium, the rate of forward reaction is equal to the rate of backward reaction. This reaction represents the synthesis of ammonia by the Haber process. So ammonia is synthesized industrially by the Haber process. Once this equation or this reaction has been established, the yield of ammonia depends on a principle. The principle is the Chatelier's principle. The Chatelier's principle. So the Chatelier's principle states that for reversible reactions that attain equilibrium, the change in external factors such as temperature, pressure, or concentration will shift the equilibrium in such a way that it's going to annul or cancel the effect producing it. So there are three main factors that influence the equilibrium position. We have temperature, temperature, pressure, concentration. So let's see factors influencing equilibrium position. Factors influencing the equilibrium position. So these factors influencing the equilibrium position, there are three of them. We have the temperature, we have the pressure, we have the concentration. So we're going to start with the pressure. Pressure. Consider the above equation as attain equilibrium. In this case, we have N2 plus 3H2 giving 2NH3. An increase or a decrease in the pressure will either shift the equilibrium position to the left or to the right. So, for this equilibrium above, the equilibrium position will shift to the right if pressures increase. Why is it that the equilibrium position will shift to the right? So, whenever a reversible reaction is given to you, you have to look at the number of moles on the left and the right. The number of moles here is 2 moles. I have 2 moles. The total number of moles here is 1 here because there's not since 1. 1 plus 3 is 4. Here we have 4 moles. Then an increase in pressure will shift the equilibrium position where the number of moles is small or the lesser number of moles. We'll compare the number of moles on the left and on the right. On the right, the number of moles is 2. On the left, the number of moles is 4. But the equilibrium position will shift to the side where the number of moles is less if pressures increase. In this case, increasing pressure shifts the equilibrium position to the right. Decreasing pressure, the reverse is true. Decreasing pressure shifts the equilibrium position to the side where the number of moles is less. So let's see another reaction or another equation. So let's see the decomposition of N2O4 decomposed to give N2 plus 2O2. So let's put a reversible reaction because the reaction is reversible. In order for us to know the effect of pressure on the equilibrium position, we check the number of moles on the left and the right. In this case, the number of moles on the left is 1. Here we have 1 mole. The number of moles here is 2 plus 1. We have 3 moles. The equilibrium position depends on the number of moles on the left or the right. An increase in pressure will shift the number of moles to the side where the number of shift the equilibrium position to the side where the number of moles is less. In this case, the equilibrium position will be shifted to the left. Why? Because on the left, we have just 1 mole. On the right, we have 3 moles. This will happen if and only if pressure is increased. Then if pressure is decreased, the reverse will occur. If pressure is decreased, the equilibrium position shifts to the side where the number of moles is more. That is on the right. Then we have some cases where pressure does not affect the equilibrium position. Example, you can have H2 gas plus I2 gas giving HI, two of them. HI is also a gas. Good. Let's check the number of moles on the left and on the right. So on the left, we have 1 plus 1, you have 2 moles. On the right, we also have what? 2 moles. The number of moles on the left and the right are equal. Pressure does not affect this type of reaction. Why? Because the number of moles are the same both on the left and the right. So an increase in pressure or a decrease in pressure will have no effect on the equilibrium position. So let's go to the next factor, which is temperature. If we talk about temperature, we're going to be talking about the delta H value. Delta H value. Consider the second equation that has attained equilibrium. We'll have 2 SO2 gas plus O2 gas. The reversible reaction giving 2 SO3 gas. Delta H is less than 0. So in this case, we are seeing the effect of temperature. Temperature. Effect of temperature on the equilibrium position. So let's see, for an exothermic reaction, if delta H is less than 0, means the reaction is exothermic. Exothermic meaning heat is released to the surrounding. For such reaction, if you increase temperature, so delta H less than 0 means the reaction is exothermic. If temperature is increased, so you increase temperature. If temperature is increased, if temperature is increased, the equilibrium position will shift to the left. Why? Delta H is negative, heat is released. An increase in temperature will shift the equilibrium position to the reverse direction, to the endothermic side, which is the left, because delta H less than 0. Whereas if you decrease temperature, a decrease in temperature will shift the equilibrium position to the right, knowing that delta H is negative. So temperature will affect either endothermic reaction or exothermic reaction. Consider the endothermic reaction below. We have C2 H plus water giving CH3 or H. Delta H equals plus 90 kilojoule per mole. In this case, delta H is greater than 0. For endothermic reaction, the equilibrium position will not be the same as for exothermic reaction. An increase in temperature here In this case, where delta H is positive, an increase in temperature will shift the equilibrium portion to the right. Why? Because the reaction is endothermic. The reaction is absorbing heat. Given that the reaction is absorbing heat, an increase in temperature shifts the equilibrium portion to the right, while a decrease in temperature will shift the equilibrium portion to the left. Then we're going to see concentration. Concentration. So let's take the reaction below. N2 plus O2 gas giving the reversible reaction giving 2NO2 gas. So here we multiply by 2. The reaction is reversible. So increasing the concentration of the reactant. That means if you increase the concentration of N2 or O2, the equilibrium portion will shift to the right. If you increase the concentration of N2O, the equilibrium portion will shift to the left. So increasing the concentration of the reactant will shift the equilibrium portion to the side where the product is. Increasing the concentration of the product shifts the equilibrium portion to the side where the reactants are found. So, because we spoke about pressure, so given that from Boyle's law, the pressure is inversely proportional to the volume. That's why I didn't mention volume, because speaking about pressure, you are indirectly speaking about volume. If you increase pressure, meaning you are decreasing volume. If you decrease volume, means you are increasing pressure. So, we are going to take a typical example. So let's take a GCE question, GCE type question. GCE type question. Consider the reaction below. Consider the reaction below. We have here we have N2 gas plus 3H2 gas. The reversible reaction giving 2NH3 gas. Delta H equals minus 90.5 kilojoule per mole. What will be the effect on the equilibrium position? What will be the effect on the equilibrium position if A, pressure is increased, B, temperature is increased, C, the concentration of N2 is increased, D, iron is used as a catalyst. Iron is used as a catalyst. So I am going to give you 1 minute. In that 1 minute, you are going to like brainstorm on what's on the board, because I'm just on explaining this example or this. So here's an example. So you guys, you are going to brainstorm on this exercise. So let me read the exercise for you. Consider the reaction below. N2 gas plus 3H2. Reversible reaction giving 2NH3. Delta H is minus 90 kilojoule per mole. What will be the effect on the equilibrium position if A, pressure is increased, B, temperature is increased, C, the concentration of N2 is increased, D, iron is used as a catalyst? So 1 minute for you guys to brainstorm on it. So I gave you some few minutes for you guys to actually brainstorm on the exercise as board. So I'll read back the exercise for you guys. The equation goes thus. Consider the equation below. We have N2 plus 3H2, reversible reaction, giving 2 ammonia. Delta H is minus 90 kilojoule per mole. The question goes thus. What will be the effect on the equilibrium position if pressures increase? B. Temperatures increase. C. The concentration of N2 is increased. Iron is used as a catalyst. So for pressure, first of all, we'll analyze the equation. We see that we have 2 moles here. Here we have how many moles into tap? 4 moles. I told you earlier that the pressure, if you increase pressure, the equilibrium position will shift to the side where number of moles is less. In this case, the pressure is going to shift to this side, the equilibrium position. Why? Because here we have just 2 moles compared to 4 moles. So the equilibrium position will shift to the right if pressure is increased. If temperature is increased, so whenever we talk about temperature, we look at delta H. In this case, delta H is less than 0. So delta H is negative. Negative delta H means the reaction is exothermic. For exothermic reaction, if you increase the temperature, the equilibrium position will shift to the left. So for here, we're going to say the equilibrium position shift to the left. The concentration of N2 is increased. N2 is found where? N2 is found on the reactant side. If you increase the concentration of either of the reactant, the equilibrium position will shift to the product side. So here the equilibrium position will shift to the right. Then for the last one, D, iron is used as a catalyst. Iron is used as a catalyst, meaning the equilibrium position will neither shift to the left nor to the right. A catalyst does not affect the equilibrium position. A catalyst is just there to increase the rate of chemical reaction. So here for D, we are going to say a catalyst does not affect the equilibrium position. So in a nutshell, that is the correction of the exercise I've given to you. So we're going to go now to our next, our next lesson, which is the equilibrium constant Kp and Kc. So let's see the equilibrium constant Kp and Kc. The equilibrium constant Kp or Kc. So consider the reversible reaction below. The reaction is small a with A plus small b with B. Reversible reaction giving small c big C, small d big T. In this case, we're going to apply the equilibrium constant. The equilibrium constant Kc is given by Kc is equals to concentration of C to the power C, concentration of D to the power D, divided by concentration of A to the power A, concentration of B to the power B. So, in a nutshell, the equilibrium constant Kc is simple. For reversible reaction that attain equilibrium, the product of the concentration of the product raised to their molar coefficient divided by the product of the concentration of the reactant raised to their molar coefficient is equal to a constant at constant temperature. So the Kc value is simply just affected by temperature. So the only factor that affects Kc is temperature. Let's see how we can calculate the equilibrium constant Kc for a reaction that has attained equilibrium. So consider the reaction. Calculate, or example, calculate the equilibrium constant. Kc for the reaction 2SO2 gas plus O2 gas giving 2SO3 gas. Given that concentration of SO2 is 0.4 molar, comma, concentration of O2 0.1 molar, and concentration of SO3 plus 0.2 molar. So let me read a question for you. Calculate the equilibrium constant Kc, here is Kc, for the reaction 2SO2 gas plus O2 gas given 2SO3 gas, given that concentration of SO2 0.4 molar, concentration of O2 0.1 molar, concentration of SO3 0.2 molar. In this case, for the solution of this exercise, we'll write back the equation. Solution. So we'll write back the equation. The equation is 2SO2 gas plus O2 gas, reversible reaction, giving 2SO3 gas. In this case now, we'll apply the formula for Kc. So Kc is equal to the concentration of the product in this case SO3. Go for the concentration of the product. It's SO3. So we have concentration of SO3. The coefficient is 2, so square divided by concentration of SO2. The coefficient in this case is 2. Concentration of O2. The coefficient is 1. Given that we already have the concentration has been given to us. We have concentration of SO2, concentration of O2, concentration of SO3. So we substitute in the equation. So Kc is equals to, so concentration of SO3, which is 0.2 square divided by concentration of SO2 0.4 square, concentration of O2 which is 0.1. Voilà. So apply. So how to punch in the calculator? So how to punch? So start by squaring the values first of all. Now 0.2 square. So that's 0.04 divided by 0.4, 0.16, because this one is 0.16, 0.16 times 0.1. Kc is equals to 0.16 times 0.1, 0.016, 0.04 divided by 0.016 equals to 2.5. 2.5 per mole per dm cube. So that's the value of the equilibrium constant Kc. So this was example 1. We'll have to solve example 2 also, so better increase your knowledge or your understanding of this equilibrium notion. So I'm going to put example 2 on the board, but before that, I'm going to brief you guys on example 1. The question goes thus: calculate the equilibrium constant Kc for the reaction 2SO2 plus O2 reversible reaction given 2SO3. Given that the concentration of SO2 0.4 molar, concentration of O2 0.1 molar, concentration of SO3 0.2 molar. So in this case, we'll have this reversible reaction Kc equals to this. We'll have our data So we replace the data in the expression for the equilibrium constant. Our final answer gives us 2.5 mole per dm cube, mole per mole per dm cube. Now we're going to take examples. Example. Example 2. Calculate. Listen. Okay. The equilibrium constant. Calculate the equilibrium constant. Case for the reaction into gas of 3H2. Yes. Reversible reaction into NS. Yes. Concentration of into plus 0.1 molar. Concentration of H2 0.3 molar. And concentration of next 0.4 molar. So example 2 is not quite different from example 1. A reversible reaction has been given to you and you have been asked to calculate the equilibrium constant Kc. So to calculate the equilibrium constant Kc here is quite simple. You apply the formula. You apply the formula for Kc. In this case, this reversible reaction is given to you such that N2 plus 3H2 giving 2NH3. In this case now, we'll apply the formula. Solution Kc equals to the concentration of the product. So I have concentration of NH3 square divided by concentration of N2, concentration of H2. So you see something is wrong in my expression. One thing is wrong. Why? Because ammonia, the coefficient of ammonia is 2. The coefficient for N2 is 1. Then what about the coefficient of H2? The coefficient of H2 is simply 3. So here we put 3. This implies we substitute our value. Kc is equals to concentration of NH3 0.4. You square it divided by concentration of N2 0.1. Concentration of H2 0.3. 0.3 cube. Kc is equals to, we take our calculator again to punch. Our calculator to punch. So having 0.4 times 0.4 equals to 0.16 divided by 0.1 times 0.3 times 0.3, 0.09. This implies is equals to 0.09 times 0.1, 0.009. So I have 0.16 divided by 0.009, 17.7. 17.7. So we have to look for the unit there. So the unit, if here we call here we have mole 1 times mole is mole square, mole foot. Mole foot cancel mole square. We're left with mole. So Kc will be 17.78. Then mole square dm to the 6. Because here we will be left with dm times 2. That is dm to the 6. Lots of indices, the cause of become positive. So now we're going to see the equilibrium constant for reaction that has attained equilibrium. The equilibrium constant for reaction that has attained equilibrium.